All right, this week we've been testing effects of temperature and UV on superhydrophobic and superhydrophilic nanostructures. My name's Katie.
I'm Jaden.
I'm Ryan.
I'm Amisha.
I'm Jonathan.
And we're
Team
1.
Okay, so you may have noticed the words superhydrophobic and superhydrophilic on the slide before. These concepts are the core of our experiment. But what do those exactly mean? Let's break it down. Superhydrophobic. They include the word phobic, referring to its characteristic of repelling liquids, especially water and other polar liquids. The coating of superhydrophobic surfaces is usually nonpolar, therefore repelling, as you can see in the lotus leaf and the self-cleaning surface on the shoe. Superhydrophilic surfaces, on the other hand, attract water. As you can see in the diagram on the bottom, the water on the surface is attracting and it's spreading out.
So contact angle is usually how we measure how hydrophilic or hydrophobic something is. The higher the contact angle, the more hydrophobic something is. So what we do is we put a drop of water and then we use a machine called a tension meter to measure the contact angle. So for our experiment, as nanoscience research is getting more and more prevalent and the applications are becoming more and more clear, we wanted to see how extremes of heat would affect these surfaces that we made, the superhydrophobic and superhydrophilic surfaces. So we used very high heats and very low freezing points to see what would happen.
Now, this directly ties into a very, very important field for all of the products that we use nowadays, which is reliability testing, which is essentially to simulate long-term use. You put any item through extreme conditions. You know, take example for a car, you would run it at like 200 miles per hour for an hour to simulate a couple months of driving. So this is really important for many different chemicals and how we use them in our applications because a lot of things that we use nowadays, especially in terms of industrial manufacturing, need to withstand long temperatures or interchanging temperatures for long periods of time. That's where our experiment comes in. Future research could develop more, in industrial applications, something that's hydrophobic that can withstand super long exposure to very high heat, or in some cases intervals of very hot or very cold exposures. And another application of this is also in airplane defrosting, where when planes fly, they're in high elevation, they have to deal with very, very cold temperatures. And so a big problem is ice forming on the wings. If you have something that can withstand that cold temperature and also retains its hydrophobic capabilities, then you now have that problem solved.
So another core concept in our experiment is nanocrystals. We began with a piece of unsanded copper. From the naked eye, it's just a piece of copper. But when we go down to the nanoscale, after sanding, we can see that small ridges form. These ridges increase the surface area, which is very important for our experiment. We then put this sanded copper into a solution of silver nitrate. The silver nitrate forms the nanocrystals, which thereby increase the surface area even more.
So after we put the silver nitrate on it, we either coat it with MUO or DCT, also known as
11-mercapto, 1-undecanol, and 1-decanothiol.
And the MUO makes it hydrophilic. As you can tell, the water is closer to the surface, and the DCT makes it hydrophobic, and it repels the water and makes it like a ball. So our question is, will heating and cooling affect the hydrophobic and hydrophilic properties of the nanocrystal and non-nanocrystal surfaces?
So we think that setting our samples of superhydrophobic / philic samples, they will probably degrade at extreme heat because all the molecules are like moving really fast and they're more prone to change. While freezing it probably won't do anything because all of them are just frozen and like not moving much.
So for our experiment, we had a total of 45 samples, which we divided into 3 groups, 15 each. The first sample group had just plain copper, unsanded. The second group had sanded copper coated with silver nitrate and DCT, a hydrophobic surface. And the third group had sanded copper with silver nitrate and MUO, making it a hydrophilic surface. We then exposed these samples to extremely hot and cold temperatures, ranging from 200 degrees Celsius in an oven to negative 271 degrees Celsius using liquid nitrogen. We also exposed some to room temperature to keep them as our control. We then measured the change in structure by comparing the previous and after contact angles.
So before we begin our experiment, it was important to note that copper in room temperature forms copper oxide. So then we had to scrape it off to bind it to the silver nitrate, which we can coat with MuO and DCT. So to create our samples, we have 45 pieces of copper. We sanded 30 of them, or 2/3, and then we coated them in silver nitrate and DCT to make them super hydrophobic and super hydrophilic, respectively. We then measured the contact angle to see what it would be at room temperature. And then we then exposed the samples to the extreme temperatures of 200 degrees Celsius and 80 degrees Celsius and negative 271 degrees Celsius to see the freezing and heating would do to them. And then we remeasured the contact angle to compare the differences.
So we had a certain amount of expected results. As we said earlier in our hypothesis, we expected the samples exposed to extreme heat to degrade and lose their properties, whether that be super hydrophobic or super hydrophilic. With cold, we expected little change, because the cold would essentially decrease the energy moving around in the samples and stop them from degrading. And with the control, we expected no change because that's the point of a control. We didn't change as many variables. One important aspect of why we expected the heat to change is not only does the heat degrade the molecules, but the heat would actually cause the copper to expand using the thermal expansion equation. However, it's important to note that this would be on a very micro scale. It only changes by a couple nanometers. But on the nanoscale and in the nanoscale structure of the silver nitrate crystals, that could have a different impact.
So for our copper plate results, we can see that the temperatures at negative 271 degrees Celsius, negative 20 at room temperature, and at 80 degrees Celsius were all about normal. But at 200 degrees Celsius, the copper actually had a much lower contact angle, meaning it would be a lot more hydrophilic. For our DCT, which is our hydrophobic results, we found that although the ones at the different temperatures had a slightly different change, the one that we expected to change at 200 degrees Celsius did change a lot, and it also became a lot more hydrophilic. For our MuO, our super hydrophilic surfaces, we found that they're almost all the same, except the outlier that our room temperature, it actually became a lot more hydrophobic and increased 34 degrees, and at 200 degrees Celsius, it did increase 50 degrees.
So let's stop for a second. What could have caused that increase in room temperature? Our MuO contact angle changed at room temperature by 34 degrees. This could make the difference between a hydrophilic surface and a hydrophobic surface, which it did. So we decided to look into the potential causes of this change leading into our second trial. So our causes, which we thought of, were atmosphere. Perhaps there were some gases in the air that could have reacted with the copper. And then there also could have been a potential of sunlight and UV radiation causing changes in the surface, which is what we tested next.
So when we tested sunlight, we saw that MuO had the greatest difference, meaning it could explain why the room temperature changed so much. And when we tested UV, we had the same result. It became more hydrophobic by 33 degrees.
So in conclusion, for our MuO, especially as we saw by the UV light, there was a drastic change between the room temperature as compared to the other tests. For the DCT, it was as expected. The DCT began to burn off at the extremely high 200 degrees Celsius temperature, but other than that, there were not many large changes. The copper plates, now this was very different from what we expected. The contact angle actually started to decrease as temperature went up, which could potentially have some future testing. And as we also saw, the sunlight and the UV light also caused an MuO change. So in conclusion, MuO is affected by sunlight while DCT and normal copper is not.
So this leads us to some future testing we could potentially do. First of all, we could potentially test the copper with and without the oxidized layer on. And then we could also test a lot more different temps, like higher than 200 or lower than, okay, not lower, but or just around the same as the one we tested. And then we could also test this with a lot of different metals that wouldn't like just degrade at 200 degrees Celsius like our control did.
Thank you for listening. Are there any questions?
So the question was why we chose copper. The reason why we chose copper is because it would bind to the silver, because we don't have a lot of money to spend on silver, so we can't just use silver nitrate and bind it with the DCT and MUO. We could just scrape the copper off and it would bind to the silver nitrate.
In addition, it's also an example of how nanocrystals and nanostructures help increase the surface area and therefore affect the superhydrophobic or superhydrophilic properties. So it pertains more to nanoscience than if we just use copper and then soaked into DCT. I mean, silver and soaked into DCT, because that's where the bond forms. The times varied somewhat, not a whole lot. Looking specifically at the super high heat, we were talking with a lot of our instructors about the implications of putting it for a long amount of time versus a short amount of time. Initially, as you saw, we had 80 degrees Celsius as our max, but as we saw, there was essentially little to no change, and so we thought, why not go to the extremes or as high as we can safely. So we put in, the samples we put in for 200 degrees Celsius, we put in at the oven, 200 degrees for 1 hour. And initially we were going to do 2 hours, but limited by time because we didn't have as much time, and also by the realization and talking with our instructors over here, especially Steven, shout out. He said that if it wouldn't be damaged for at 200 degrees Celsius in 10 minutes, it wouldn't really change that much for 2 hours. But we wanted to keep some consistency because the 80 degrees samples we had in for 2 hours. So we wanted to at least have it for a long time from, so that's why we kept it in for only 1 hour, and we did see a very significant change. Oh, and someone else want to cover the future implications?
Oh, yeah. So what we want to see was basically that we wanted to replicate how a long period of time at a relatively normal temperature, but we couldn't exactly do that due to time limitations, so we did an extremely high temperature in a very short amount of time. In the future, perhaps when we do have more time, we could try it with larger amounts of time at a normal temperature to see if it replicates the results that we found earlier.
In addition, another thing we were thinking of doing that we couldn't do according to time constraints is intervals between high heat and low heat, because that change could potentially degrade things a lot more than just being exposed to one temperature consistently. Stephen?
Sulfur bond. The only difference is 7 or 8 carbons later, there's an OH molecule. How is that allowing UV light to degrade NuO, but not DCT?
We don't know, but we have a couple guesses. Of course, this is relatively uneducated because, I mean, we've all taken chemistry at one point, but of course we're not experts. At least personally, I know my assumption was that somehow the OH on the end could have somehow reacted with the UV light and maybe degraded the rest of the chains, or maybe somehow affected the sulfur bond, making it less polar or affecting the polarity in some sense, or using up electrons or something like that. It could have been a lot of different things. We don't know. That's one of the things that we would have to do a lot of future testing to figure out.
Oh, that's actually a really good answer. I was thinking the sulfur was coming off, but yeah, it might actually make more sense if the OH just binded with something else, making it less.
Yeah, I mean, it's just because the molecules are almost identical. Sorry for not clarifying earlier. MUO and DCT are essentially the same molecule. One is just polar on the end, and the other isn't. So that's why we use these two, because they're very similar. Yeah, maybe. A lot of different stuff to do. A lot of future testing is needed.